In this video, we are going to see binary frequency shift keying. In this binary frequency shift keying, the symbol 1 and symbol 0 are differed by sending them two different frequency of sinusoidal signal. Here, Si of t is the sinusoidal signal. Here, Si of t is equal to square root of 2 Eb divided by Tb cos 2 pi Fi of t 0 less than or equal to t less than or equal to Tb. Here I value is 1, 2. Here Eb is the transmitted signal energy per bit and the frequency Fi is equal to Nc plus 1 divided by Tb. Nc is the fixed number of integer and I value is equal to 1, 2. The symbol 1 is transmitted. Symbol 1 is represented by S1 of t and symbol 0 is represented by S2 of t and FSK signal is described here. It is the shunt FSK. It has the continuous phase signal and then the phase is maintained between the signal. The most useful form of set of orthonormal function is given as pi I of t is square root of 2 divided by Tb cos 2 pi Fi of t 0 less than or equal to t less than or equal to Tb. I value is equal to 1, 2 and the coefficient is equal to Sij is equal to 0 integral of 0 to Tb Si of t into pi j of t into Tb. Here integral of 0 to Tb square root of 2 Eb Tb cos 2 pi Fi of t square root of 2 divided by Tb cos 2 pi Fj of t. Here Sij is equal to square root of Eb when I equal to j and 0 when I is not equal to j. Unlike the binary PSK, this binary FSK having two basis function. It is the two-dimensional function and n is equal to 2 and with the message point m equal to 2. The two message point is defined in vector Si equal to square root of Eb comma 0 and S2 equal to 0 Eb. The Euclidean distance Si minus S2 is equal to S1 minus S2 is equal to square root of 2 Eb. And then we see this is the signal space diagram for binary FSK system. In this, this is the this is the S1 of t and S2 of t. Binary 0 is represented by S2 of t. Binary 1 is represented by S1 of t. Here this is the sample point. Sample point is equal to EB comma 0 and 0 comma EB. This is the two basis function pi1 and pi2 is the two basis function and these two message point is separated by the distance of 2 square root of eb and here this region is considered as this is the decision boundary, and this is the region 1 and this is the region 2. Generation of binary FSK signal. Here binary data sequence is given into the on-off level encoder. Here 0 means it will be off and 1 means it will be on. And here this is the m of t. The m of t signal is multiplied with the basis function with the frequency f1 of t. And then here in it has two oscillator. Oscillator in the upper oscillator is transmit the signal 1 and lower oscillator is allow the signal 0. Here the on-off level encoder, this inverter is invert the given signal and then the given signal is multiplied with the pi 2 of t, that means second orthogonal basis function and then these two signal is summed and the output is produced to the channel. The output is binary FSK signal S of t and on-off level encoder. The on-off level encoder, the output which is constant, the input is 1 and the input is 0 with the on-off level encoder. The output of the on-off level encoder is 1. It will produce constant amplitude when the symbol is 1 and 0 when the symbol is 0. and then pair of oscillator. There is two different frequency pair of oscillator is used to F1 of t and F2 of t. This F1 of t and F2 of t is different in the multiple of bit rate 1 by TB, and lower oscillator frequency is F2 and it is proceeded with the inverter. The signal interval is when the signal interval is input is one, simple 1 is transmitted at the time upper oscillator frequency F1 is switched on and S1 of t is transmitted while the lower oscillator is switched off. On the other hand, input is 0 at the time upper oscillator is switched off and lower oscillator is switched on, and S1, S2 of t signal is transmitted. With the phase continuity, the two oscillators is synchronized with each other. This is the coherent detection of binary FSK signal. Here, the output of the channel is given into the input of the coherent detector S of t. This x of t is multiplied with the pi 1 of t and pi 2 of t, and then it is given into the correlator, the integral of 0 to tb into t, and then the output of the two correlator is given into the summer, that means comparator. Comparator compare the output value is equal to y equal to x1 minus x2. The decision device will take the threshold value. The threshold value is taken as 0. If the difference between x1 minus x2 is greater than 0, then the output is the decision device take the output is equal to 1. If x1 value minus x2 value is less than 0, then at the time the output of the decision device is equal to 0. Here the coherent detector, it is the received signal is noisy. The received signal is represented as x of t. It has two correlator with common input and locally generated reference signal pi 1 of t and pi 2 of t. The correlator output is subtracted from on each other. The y is compared with the threshold of 0. If y is greater than 0, then the receiver decide in the favor of 1. If y less than 0, the receiver decides in favor of 0. If y is exactly 0, then the receiver make the random guess. The error probability of binary FSK. The observation vector x has two components x1 and x2. x1 is equal to integral of 0 to tb x of t into pi 1 of t into tb. x2 of t is equal to integral of 0 to tb x of t pi 2 of t into tb. Here x of t is the received signal. Here whose form depends on the symbol was transmitted. Here, the symbol 1 is transmitted. X of t is equal to S1 of t plus W of t. W of t is the white Gaussian noise with 0 means and power spectral density is N0 divided by 2. If the symbol 0 was transmitted at the time, X of t is equal to X2 of t plus W. And by applying the decision rule, the coherent deduction the observation space is partitioned into two regions labeled as Z1 and Z2. And the decision boundary is separating the Z1 and Z2, which is a perpendicular bisector of the two message joining point. The receiver decides favor of symbol 1 if the received signal point is fall onto the region inside the region Z1. This occurs x1 is greater than x2. On the other hand, x1 is less than x2. The received signal is fall on the region Z2. The receiver will decide the favor the symbol 0. On the decision boundary, x1 is equal to x2 at the time the receiver is randomly guessed in the favor of symbol 1 or symbol 0. Now the new Gaussian random variable y is introduced. And here y is equal to x1 minus x2. The conditional mean for random variable y for given 1 is transmitted at the time e of x1 bar 1 minus x2 bar 1. Here x2 bar 1 is equal to 0. Here e of y bar 1 is equal to plus db. Here for the symbol 0 is transmitted at the time the random variable x1 and x2 have the mean value is equal to 0. Here the conditional mean for y the random variable y given that the symbol 0 was obtained at the time e y of expectation of y of 0 is equal to x of e of x1 bar 0 minus e of x2 bar 0. This e of x2 bar 0 is equal to minus eb. This term will be goes to 0. The variance of y is equal to n naught. The conditional probability density function f of y when 0 is transmitted. The conditional probability density function of random variable y is given that fy of y bar 0 is equal to 1 divided by square root of 2 pi n naught exponential of minus y plus square root of eb divided by 2 n naught v whole square. Here, now the conditional probability of error P10 is equal to P of y is greater than 0 when the symbol 0 was transmitted. Here, P of integral of 0 to infinity fy of y bar 0 into ty is equal to, here we substitute this function into this function. At the time we will get 1 divided by square root of 2 pi n naught integral of 0 to infinity exponential of minus eb plus y plus eb divided by 2 n naught into tb. Here we take this y plus eb divided by n naught is equal to z. Y plus square root of AB divided by square root of N naught is equal to Z. If we substitute in this equation, then we will get P10 is equal to 1 divided by square root of 2 pi integral of EB divided by N naught infinity exponential of minus Z square divided by 2 into dz. And then the error function Q equal to Q of square root of EB divided by N naught. Here, we may show that P01 it is the conditional probability of error given that the 1 is sent. The average probability of error PE is equal to Q of E square root of EB divided by N naught. Power spectrum of binary FSK signal. FSK signal has two frequency F1 and F2. These two frequencies is differed by the amount of equal to the bit rate. Here S of t is equal to square root of 2 EB divided by TB cos of 2 pi FCT plus pi t divided by TB. If we expand this cosine function cos A plus or minus cos B, at the time we will get the function is square root of EB divided by TB. EB divided by TB cos of pi t divided by TB cos of 2 pi FCT plus or minus square root of 2 EB divided by TB sin pi t divided by TB sin 2 pi FCT. Here, this first term is the in-phase term and second term is the quadrature phase term. In this in-phase term, it is independent of the binary sequence. This quadrature phase term is depending upon the binary sequence. Here, during the symbol 1, at the time minus TB is C is G of T. During the symbol 1, minus G of T signal is transmitted. During the symbol 0, plus G of T signal is transmitted. G of T is equal to square root of 2 EB divided by TB sin pi T divided by T. This is the G of T signal. If we take the energy spectral density of G of T is equal to psi of 8, psi of F is equal to 8 EB dB cos square pi TB F divided by pi square 4 TB square F square minus 1. Here, FSK signal is equal to sum of power spectrally of two components, that means in phase component and then quadrature phase component. SP of F is equal to EB divided by 2 TB del of F minus 1 divided by 2 TB plus del of F plus 1 divided by 2 TB plus here we substitute this digit by psi of F 8 EB TB cos square pi TB F divided by pi square 4 TB square F square minus 1 the whole square. Here this is the power spectral of FSK. Here in this FSK at 1 by TB time period the delta function is occurred. This is the delta function, this is the in phase component and this is the quadrature phase component. Thank you.